today's talk is about measures of consciousness. And as a mathematician, it's always interesting when the computer doesn't work. Sorry. It's always interesting to start from mathematical definition of a measure. So we'll appeal to measure theory here. So measure theory, it's used obviously like in physics, also in mathematical analysis, etc. So it's useful to recall this definition. So let X be a set and sigma be a sigma-algebra over X. What is a sigma-algebra? It's a collection of subsets of X that is closed under set operations, basically. For at least for us, that definition will do because we're going to actually restrict ourselves to finite systems anyway. So then you have some function mu, which is mapping from the sigma algebra to the extended real line. And mu is going to be a measure with respect to measure theory. If it is non-negative, takes a value 0 on the empty set. And the last thing here is additivity. It has this additivity property. So for all sequences of pairwise disjoint elements of the sigma algebra, the measure of the whole is equal to the sum of the measures of the parts, essentially. So you can think about that sort of intuitively. You have a bag of sugar. You can weigh the bag of sugar, or you can weigh the individual grains of sugar and then add all that together and you'll get the same number. Okay. However, it's reasonable in consciousness science to assume that measures of consciousness are not actually measures with respect to measure theory because of something called superadditivity. So you think about going from sets to systems now. You think about a brain, we would anticipate that the consciousness is likely connected to all of the interconnections within the system. So when you measure the amount of consciousness of a brain, it's going to be much more than 80 billion times the amount of consciousness of a single neuron. And of course, IIT, big phi in IIT is superadditive, of course. So the definition of a measure in measure theory doesn't come over to consciousness measures in general. And I have this little extra note on the bottom here that actually superadditivity can be used as a useful definition for a type of emergence. Obviously, going to be a weak type of emergence as well. But I just couldn't resist to mention this because I always like to give formal definitions of things. And there's just one there, which is just given for free, if you like. But it's not about, this talk is not about that. Okay, so, however, there may be situations when actually the measure theory definition does have some relevance. So suppose phi mock is any proposed formal measure of consciousness. So it's not phi from IIT anymore. It's could be anything, any such measure. Well, we've already said that it's not going to be a measure with respect to measure theory because of superadditivity, but in principle, it should be able to measure anything. You should, in principle, in practice, perhaps not, of course, but in principle, you should be able to apply it to all sorts of kinds of systems, and that includes systems such as systems made up of pairwise independent subsystems. So particularly, I'm thinking about things which we're kind of familiar with. So take this room, for example. You could say this room or all the people in this room is my system. So this is made up of pairwise independent subsystems, or the animals at the zoo, or more generally, other finite systems with pairwise disjoint, independent, large, complex natural systems in some sense. In this case, maybe the definition has some relevance. So, we can think, for example, of a nest of ants. Well, maybe these ants are social animals, and so they're not really independent. So let's just make sure that they are independent. And for ants. So let's just now do what we just did again, but we're going to do it in more formal terms. Don't be put off by the mathematics here. I will explain it. It's really very simple. So again, let phi mock be any proposed formal measure of consciousness. Let S be a finite system with pairwise disjoint, independent, large, blah, 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 subsystems, and let chi S be the set of these subsystems. So remember, it's a set of subsystems. Then we can define the sigma algebra generated by chi-s. And how do we do that? It's really very simple. You just think of all possible ways of grabbing some subsystems from chi-s and then just taking them together as a new system. And you just define the set of all such systems that you can then generate from what's inside chi-s, those independent subsystems. So for example, going back to the ant nest analogy, well, it would be all possible subsystems of the ant's nest, but under the constraint of maintaining whole ant granularity. So you're not allowed to have half an ant's system in one of these subsystems. It's got to be. So in this case, the measure theory definition should dominate when restricting the measure to sigma chi-s. So this sigma-algebra that we have generated. So for example, the measure of the ant's nest is going to be more or less equal to number of ants times the measure of a single ant, for example. Okay, so the next slide, I'm going to give a practical example from my own work of how you can actually have such measures turn up in our field. So the top half, let's look at the top half of this slide to start with. So there's a little bit of background on this piece of theory, which is now, I think, 12 years old. It's been in the literature for quite a long time. Starting point is that the brain, according to this theory, is defining two things. One thing, obvious, it's defining its system states at any given time. But the other thing is that somehow the system must be defining some kind of interpretation of its own states as well. So state plus this interpretation gives you consciousness. Okay, and motivation for this, think about when you are asleep, you can be dreaming, and you can be dreaming of being in this room, and you'll have colors and everything else, but there's no image on the retina at all. And so this is a property of the brain itself. So the brain is somehow defining the geometry of the field of view, color space, and so on. Although you're in a dark room, there's nothing on the retina at all. So this, so it has a state, it must be somehow defining an interpretation of that state. And similarly for inner sound. Now, turns out, if you look at this at the bottom now of this slide, on the left-hand side, almost all interpretations are like this. It's just random noise, garbage. So almost all interpretations are just noisy, mixed up stuff. The one in the middle is a bit better, but actually the one which kind of looks like we kind of recognize as being like our consciousness is this one on the right-hand side. And in some sense, it's low entropy. So it has lots of order and structure to it. It's not just a scrambled up mess. So yeah, so my work, it kind of comes from basically sort of postulate. So a few things on here. This is the system itself, an important point. Because of all of the wiring in the brain, it's biased towards certain states over other states. Okay, so I'll just read out this postulate. So if we suppose that consciousness is given by an interpretation of system states, then among the infinitely many possible interpretations, consciousness is given by some form of minimum expected entropy model interpretation of system states that yields experiences free of unnecessary discontinuities whilst exhibiting intrinsic structural regularities in probable system states. So the probable system states is coming from the fact that the brain is very biased towards certain states over other states. So that's our kind of hypothesis behind this piece of theory. And of course, as a mathematician, you then take the hypothesis and you translate it into the mathematical domain. This goes back to 2012, this part. This is slightly simpler than the whole theory for sure. So it talks about primary models. So instead of defining the whole interpretation, we're talking about sort of hierarchy of relational models that are being defined, but we're only going to be looking at the sort of primary level, the bottom level, because it's just simpler for the purposes of this talk, etc. But there's other work which involves things at higher levels within the model and so on, within the interpretation. So what is this here? It's actually very straightforward, really. So R and U are a part of the interpretation. They are a relational model, R and U. And R is, for example, on system nodes, it's a relationship between nodes. U is a relation on node states, the states that the nodes can be in. And then F is a system state. It is a state of the system. So, well, what is this? Well, basically, what you really need to know from this is that when the model is a really good model for the particular system state that we're interested in, so F, relative to other system states. So this is an important point. It's that the model is a really good fit for this system state relative to other system states. Then you get a small value from this. This is what you get from. We call this float entropy. So it has people who know maths, it's got a log, it's got a number of things in it. It looks like a sort of entropy type expression. And then we extend this because remember our system has got system bias, which we represent as a probability distribution. So now we can simply take the expected quantity of this over the system states. So we get expected float entropy. And then in this expression at the bottom of the slide, we use this curly notation to denote the model that is best in some sense. This is the model that gives the minimum expected float entropy. So when you see curly notation in slides to come, then you know that it's meaning that they are the optimal parameters under this requirement for minimum expected entropy. Float entropy, I should say, float entropy. Okay, so lots on this slide, don't be worried. We're going to extend the definition from the last slide just a little bit more. So we've done the minimization over all possible models. We now do it over all possible ways of viewing the system as a collection of subsystems. So we're doing two things simultaneously. We're finding the best way to view the system as a collection of subsystems and the best possible model. We're doing this optimization over both things. So when you see EFE hat, this means that we're also doing the optimization over viewing the system as a collection of subsystems. When I say view it as a collection of subsystems, I don't mean like in IIT that we are chopping the system up. I'm just saying that you can just view it as a collection of subsystems. Okay. And so we did a paper which came out in 2021 on model unity and the unity of consciousness. And we did some examples using digital photographs to sort of test this out. And with respect to the tests that were undertaken in that paper, turned out that indeed under EFE minimization, systems with independent subsystems partitioned accordingly. So the model broke down with respect to matching the granularity of the independent subsystems. So each independent subsystem essentially got their own model, their own interpretation, rather than having just one stretched across the entire system. Now, there's a dagger there. I'll use that dagger to refer back to this point because this is not a proof in general. We're just saying that it worked great when we tried it with respect to these tests that we did. And so it's an assumption that it would work always or on a much, much larger range of experiments. Okay, so at last, we're getting to the point where we're able to define a measure at last. Okay, wonderful. So I'll probably just read out this slide. So let S be a finite system with pairwise disjoint independent large complex natural subsystems, and let chi-S be the set of these subsystems. Again, we define the sigma algebra, sigma chi-S, generated by the subsystems. And then we can just take a sampling of sigma chi-S under the requirement that subsystems are pairwise disjoint. Okay, then in this case, we can define this measure such that when you have the empty set, the measure is just 0. If I have to do this because actually if I use the term below, it would be undefined. You would like have infinity minus infinity. So we just take it to be 0. And then this, with respect to the system, which is the union of these subsystems, then we use this definition. So it's the log of the number of possible system states that the system has. So this omega is the set of all possible system states in this case, minus this EFE hat that we defined earlier. And then in this case, assuming this dagger from the last slide that you may remember, it holds that this is a measure in the measure theory sense of a measure when restricted to sigma chi-S. So not in general, but when you restrict it to sigma chi-S, then more or less it looks like a measure from measure theory. And okay, first mathematical proof of the conference. So I couldn't resist but to actually show the proof. If you're a mathematician, you'll look at this and think this is so trivial. Why did Jonathan bother putting the slide up? But for those who, for everybody's benefit, then I will just really quickly go through this proof. And so the top line is simply the definition from the previous slide. The line below, you can see that inside the log, there's something has changed. Well, it's simply that if you have two independent systems, or if you have a system which is made up of, say, two independent systems, then the number of states of this thing as a whole is simply the product of the number of states of the two independent systems. So that's all I've done there, just express it as a product. The second term on the second line is just given by the definition of EFE hat. The line below, we are just applying the log laws to get a summation with respect to the first term. Second term is the same as the line above. The line below that, we're just collecting terms together. And then at the end, this is basically just reversing back to what the definition of sigma phi EFE is. So indeed, you see that this is indeed an example of a measure which is additive when restricted to sigma chi-S. So I went through that quite quickly. I think I am on time with probably a couple of minutes left on the clock, which is fine. So I just explain then, what is the point then of this example? Essentially, I'm not trying to say that this is a fantastic measure of consciousness, which we should all adopt in preference to IIT, Big Phi and IIT. It's really more of a message that when thinking about measures of consciousness, what you can do is you can think about the mathematical properties that such a measure should have. And then when developing it, actually look to see whether the measure has these properties as a guide. And actually in the questions, I would like to know whether people think that the actual underlying assumption in this talk is actually one which you would agree with, that if you have a system made of independent subsystems, then the consciousness measure on the system as a whole should be additive over the independent subsystems. So thank you very much for listening, and